तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were looking at the elasto-plastic behavior and we were determining the tangent stiffness matrix. So, if there is any question, let us discuss. If there is any issues here, let us discuss them. Yes.
Suppose if the material is under both in the elastic and plastic region, just we are applying the load, it is in the region where the curve changes.
Yes. So, in other words, this equation is valid in the elasto-plastic region. Note that this equation is valid in the elasto-plastic region. Obviously, since we are going to go through an incremental procedure, we will pass through the elastic region and then go to the plastic region, right. So, in the elastic region, this equation is not valid, okay, and we will use only Et is equal to E. We will use only Et is equal to E. So, you will see this maybe in the next class or after that we will develop a procedure and you will see that we will constantly be monitoring whether yielding has taken place, okay, or in other words whether we are in the elastic region or in the plastic region. To preempt some of the things which we are going to do later, you know that there are what are called as Gauss points in the elements. Okay, there are what are called as Gauss points. Yes, that is used for numerical integration. These Gauss points that are used for numerical integration have certain internal variables or history dependent variables, okay, as a part of the program. So, if you look at, say for example, if I use 4, then I will have 4 different arrays per element of history dependent variables stored. One of them can be called as a yield switch. One of them will store the plastic strains, one of these internal variables. One of them will store the yield strength and so on. So, we will be monitoring continuously as to where the element is, or in other words where the Gauss point is with respect to the stress strain curve. So, once we know that for this Gauss point the material is in the elastic region, then we will not use this equation, but we will use E, go back to the stiffness matrix for the elastic case. If this, say for example, it is possible, it is quite possible that this may be in the elastic region and this Gauss point may be in the plastic region, in which case when I calculate the stiffness matrix and when I come to this Gauss point I will use Et, and when I come to this Gauss point I will use E. Is that clear? Or in other words, there is going to be a jump even within an element. So, this causes some other mathematical issues, we are not going to discuss that, but this is a very important implementation issue. So, that is why we in all of the nonlinear codes we have what are called as history dependent variables. People usually distinguish between history dependent, history in the sense that the path that it has taken has a bearing on these variables, that is what we call as history dependent variable. People distinguish between this history dependent variable and history independent variable. That does not change as we go on in the solution of the problem, it does not change, it remains a constant, okay. That is called as the history independent variables. We will see more of it as we go along in this course, but it is very important to realize that I will use appropriate things at appropriate places. Yeah, the next question is that what happens when h goes to 0. So, h goes to 0, what happens? The stress strain curve, in fact you can see that when h goes to 0, this guy becomes 1, so Et becomes 0. In other words, stress strain curve takes a turn like that, right. So, this is what we call as elastic perfectly plastic. You know that this curve is the result of what is called a strain hardening, and that this curve neglects strain hardening characteristics. So, we call this as perfectly plastic. In many problems, especially when we deal with forging problems, we may not be interested in the elastic part. Please note that I have exaggerated the slope. Actually, the slope will not be as high as that. I told you in the last class itself, the slope will be very, very close to the y-axis, and hence in many problems it may be possible to treat the elastic part to be absent, to make an assumption that the elastic part is absent, and treat the problem itself as rigid plastic. Rigid in the sense that there is no elastic part. Okay. In the elastic part it is rigid, or the strains in the elastic part is so small when compared to the total strains, we can consider that as rigid. So, rigid plastic, rigid perfectly plastic, combination of this and rigid. Rigid means it just goes like that, and so on. So, these are the assumptions that we make in certain problems, right, and this, of course, this judgment is very important and comes from our engineering knowledge. So, of course, depends upon the problem. Okay. Now, having said this, let us see how we derive the stiffness matrix for a simple bar. Okay. So, we said that we should start with that B transpose sigma. We had already seen that this whole stiffness matrix K can be written as B transpose dt B d omega. So, what would happen for a one dimensional case? Even looking at it, you can say that there is no big problem. Okay, looking at it, you can say that the tangent stiffness matrix for a one dimensional case now can be written as, what was it before? It was AE by L. In the previous case, it was AE by L 1 minus 1 minus 1 1. Note that we are just considering a bar element. Okay, the previous case it was like that, and now since that d has been replaced by dt, E is replaced by its corresponding material parameter Et. So, A is equal to Et by L into 1 minus 1 minus 1 and 1. Is that clear? Okay. Now, having said this and having seen how we look at other issues, let us do a problem, but before that I just want to bring out one more point which we will elaborate in the next class, that please note that the points, the stress strain should be such that the points which depict the stress strain should lie on the graph. Okay, I can't get a point here, a combination of stress and strain which lies outside or not in this graph, outside the graph. It's not possible. So, the point should lie in this stress strain curve, the graph in sense that curve rather, stress strain curve, right. So, we have to have some special procedures. We will talk about that in the next class, but let us now do a problem to understand all the steps that are involved in the nonlinear procedures. Now, take a look at this problem. This is just a bar, right, just a bar, and the length of the bar is 5, the area is 1, The load that is applied is 4.8, and look at the stress strain behavior, 20 into epsilon minus epsilon squared. So that means that the behavior is nonlinear, right? And apply the load 4.8 in 2 increments. In other words, in increment 1, apply a load of 2.4, and in increment 2, apply a load of 2.4, okay, further to the first 2.4. That means that the total load is equal to 4.8, right? We are assuming 2 increments. We are assuming, so the question is, how many increments do we assume? We are assuming 2 increments, okay, 2.4 and 2.4. Yeah, in other words, I have just given it as 2.4. Okay, you can have less as well. Okay, 1.2 to be applied in the first increment and so on. It doesn't matter, just because I do not want to take much time. Every increment is going to take time because I have to iterate in every increment. So I've just given 2.4 and 2.4, right? Okay. So the first thing that we do in this problem is to calculate ET. So what is ET? Yeah, correct. So ET is equal to d sigma by d epsilon. So that is equal to 20 into 1 minus 2 epsilon. So obviously now ET is a function of epsilon. You can see that ET is a function of epsilon. So ET has to vary, okay, as we go along in this curve. Right. So you have all your calculators with you, and so we'll start the problem. Right. So you already know what is the stiffness matrix. The only advantage here is that if I choose one element, if I choose just one element, then I have from the stiffness matrix one row and one column eliminated. Okay, so I'll have just one value in order that I should solve the problem. I mean, in order that I can simplify the problem. So the solution becomes easier. I can choose 2 elements, it does not matter, but only thing is it's going to take a lot more time. So let us choose only one element and eliminate one of the u's. So suppose I call this as element 1 and element 2, element 1 and element 2. I can write down my stiffness matrix to be node 1 and node 2, sorry, not element 1 and element 2, node 1 and node 2 for this element 1, then I can eliminate one of them because u1 is going to be fixed or u1 is equal to 0. So those two are eliminated. So I have a simple equation of the form K22 u2 is equal to F2. Of course, this is equal to F. Right? So just only one value has to be determined as we proceed in this problem. So we start now with the first increment, increment 1, with load of course equal to 2.4. Okay, let me go back to my initial symbol of F, because I think to be consistent with what we did, so there's no confusion. So the load is usually given in all problems as P. Let me go back to my previous symbol F. F is equal to 2.4. Right? And we start the iterations now. So iteration number 1. Right? So you calculate first, of course, AET by L. okay, and that is going to be my stiffness K22 for the first iteration. Please calculate that, and that multiplied by U2 should be equal to, for the first iteration, should be equal to the force. Basically because I have to calculate psi, okay. So since F is equal to 2.4, okay, the first increment I have the error psi to be the load itself, because there is no internal force that is acting. So I start that with the first iteration and increment. So this I will call this as the iteration and that to be the increment. Okay. So AET by L is what I have to calculate. So that would give me KT. So what's that value? KT, okay, because AET by L into K2 is equal to K22 is equal to 1. So this is going to be 1. So this will straight away give me one value of KT, and that is equal to 4.0. Is that clear? So that's the first step. Calculate KT. Okay. So the second step is to calculate delta U. Okay, let me call this as du. I have a reason for it. Let me call this as du. Yes. I just substituted A, Et, epsilon is equal to 0. So this is equal to 20. Okay. Please note from here that Et is equal to 20 into 1 minus 2 epsilon. Epsilon is equal to 0. So I got 20 here. So 20 goes into this place. This is 20. A is equal to 1. L is equal to 5. So 20 divided by 5. So 4. Is that clear? Okay, calculate du. One, that is equal to my psi is equal to 2.4. 2.4 divided by 4. That is equal to 0.6. Right? Now, the third step is to calculate the total strain, okay, from the total displacement. In this case, the total displacement happens to be, that is total displacement in the sense that total displacement from the last increment, which we called as delta U, not U, delta U. So in this case, because it happens to be the first increment and as well as the first iteration, we have that to be equal to du 11, okay, or else I have to sum them and put a sigma here. We will do that in the next iteration. So I have to calculate delta U, and this happens to be in this case 0.6, and from this I can calculate delta epsilon, and what is delta epsilon? Yes, we get this from B matrix. Okay, for this case, the B matrix happens to be minus 1 by L, 1 by L. Okay, that is the B matrix for this bar element, and hence that happens to be 1 by L. So 0.6 divided by L is 5, so 0.12. Right. So this happens to be 0.6 divided by 5, that's equal to 0.12. Yeah, so this one I obtained delta epsilon, obviously delta epsilon, I just write it here separately, B delta U, okay, with appropriate R and N. So now this B happens to be the strain displacement relationship, and that happens to be minus 1 by L, 1 by L, and so we have 1 by L there. The first one is for U1, U1 is equal to 0, so U2 is determined from that quantity, and hence I have 0.6 divided by 5, 0.12. So that's the next step. So having done that, what's my next step? Fifth step. Fifth step, no, I have not, it is not that we determine KT, I have to now still determine stress, I have to look at the error, and then only I have to decide whether I have to go to the next step. Okay, right? So usually it's a good practice at this point to calculate the total epsilon. Now total in the sense not only for this increment, but total till this increment. Okay, I'm going to use this total in two sense. Total epsilon means total epsilon for this increment. So I will call this as total epsilon for this increment, which means that it's a sum of du's and then B is applied to it. Okay, that's what I mean by total epsilon or delta epsilon. Okay, then total epsilon for the whole of the analysis till now. Okay, that is what we call as epsilon. Okay, so epsilon in this case 1 1, that happens to be for this case the same as what it is. Okay, so 0.12. The next step is to calculate the stress due to this. So let me do it here. So how do I calculate stress? Sigma is equal to 20 into epsilon minus epsilon squared, and that happens to be how much? 2.112. So that happens to be 20 into epsilon, you put that 0.12 minus 0.12 squared, and that happens 2.112. So clear? Have a look at it. See, this part is usually called, this calculation of stress part is usually called as stress update. This may be a very elaborate procedure when we come to elasto-plastic analysis, because you may not have a beautiful relationship like this, and I have to satisfy what I called just now as a consistency condition. That is, the point should lie on the curve. Okay, so this is usually called as the step, this step is usually called as the stress update algorithm. This is a step which is very important. A lot of research has gone in to develop various algorithms for the elasto-plastic case. Is that clear? Okay. Now, of course, the next step is to see internal forces and the error. The internal force in this problem happens to be very simple, because we are considering only one element problem. So it is just equal to sigma into A. A happens to be 1. So the internal force happens to be 2.112, and hence error is equal to 2.4 minus 2.112. So what's that? 0.288. Right. We'll stick to 3 decimal places just so that we don't keep writing it. We're going to do a hand calculation. So we'll stick to 3 decimal places, or else 3 decimal places, and then we will see that the error, we'll monitor the error and see that if the error comes to 1 into 10 to the power of minus 3, we stop the further iterations. Now, have a look at this 0.288. Obviously, it's better than my 2.4 from which I started. Not still happy with it. So I have to go over to the next iteration. So I start with iteration 2. So my increment is 1, but my iteration is equal to 2. Is that clear? So I have to redo all these steps. Okay, tell me what is now the KT value. I'll just remove this, see what the steps are, and see what is the KT value. Now, in order to determine KT, first you have to find out ET. Okay. Now, ET is from this figure. Let me write ET here. ET is, what's that? 20 into 1 minus 2 epsilon. From this, please calculate KT, substituting ET into my A ET by L, and that happens to be 3.04. Is that correct? Yeah. So that happens to be 3.04. Right? Okay. Now the next step, of course, is to calculate same thing. The only thing is that now I'm going to shift this guy here to 2. This 1 becomes 2 now, and I have to replace both these. So psi happens to be now 0.288 divided by 3.04, and what's that? 0.095. Right? Clear? Fine. So now I calculate delta U2 by adding 1 plus du 2 of 1 0.695. It's always a good practice to calculate delta epsilon from delta U. Note this carefully. There is a small subtle point here, that we calculate always delta epsilon from delta U, though for this problem it won't make a difference, but you will notice in the next series of problems that we are going to do and discuss on elastoplasticity, that's going to make a difference. So let us stick to the same procedure. So delta epsilon is now calculated from 0.695 itself. Here it can add it, it doesn't matter, but you will see that this procedure is not valid in the elastoplastic case. We will discuss that when we come to the elastoplastic case. So we will stick to the procedure, so that what I do is to get to ET 6. B into 0.695, that is my 0.695 divided by 5. 0.139. Okay, is that clear? So now epsilon happens to be, my epsilon happens to be, yeah, of course this I have to change to 2, and here I'll change to 2. So in this case the epsilon happens to be the same, 0.139. Now calculate sigma. Calculate sigma. So what you do is, instead of 0.12 here, substitute for, so the sigma which was for 1 and 1, okay, now is for 2, and that happens to be, calculate that. Pardon? 2.394. So what is the error now? So this will become 2.394. So the error is 0.006. Is that right? 6 into 10 to the power of minus 3. I'm still not happy with this, because I said I will keep repeating these steps until I get 1 into 10 to the power of minus 3. In other words, the 6 reduces to 1, less than equal to 1. Okay. So I go back and do the third iteration. Increment number 1, still we are in increment number 1, but we do the third iteration. Now this is now in the third iteration. What is the error which we calculated? That is 0.006. So that becomes 0.006. I hope the procedure is clear. Okay. Any questions? Okay. Now calculate ET and calculate KT. The new KT we have to update. We are doing full Newton-Raphson procedure, and hence calculate KT and tell me. Yes? KT is 2.888. Very good. 2.888. Now I calculate du2, so I change all these things. So I have 0.006 divided by 2.888, and what is that value? So note that I have to change this. We are now in third iteration, still in first increment. 0.002, which means that I add here du 31, and the total delta u happens to be what? 6.697. 0.697. So delta epsilon we calculate, 5 becomes now 7, and the corresponding value here. Of course, for the third, sorry, here again you have to go to 3, here again you have to go to 3. One, 3, 9, 4, 1, 3, 9. Right. Calculate now the stress. Calculate the stress. 2.399. I'll give you a minute. Please have a look at it. See how we are doing it. I hope you are not lost in the calculations. Okay, see what we are doing, how we are doing it. So note that we are in 3, so that should be 3. Right. Now what is the error? The error now becomes .399, and hence the error is 001. So I am happy with this error, and I am not going to proceed further for this increment. I say that I have achieved convergence. Is that clear? First increment is over.
So this when to stop is purely based on engineering judgment.
Now when to stop, or in other words, the question is when do we stop? What is this error? It is not based on engineering judgment. It is based on the numerical error and the corresponding accuracy of the results. So in other words, what it means is that if I can make this error 10 to the power of minus 8. Okay. Newton-Raphson procedure has what is called as a quadratic convergence rate. So if everything goes on well, if you have formulated the problem correctly, then you will hit 10 to the power of minus 8 maybe in the next iteration itself. Okay, next increment or next iteration itself you will hit it. Okay. In other words, the number of iterations between 10 to the power of minus 3 and minus 8 may not be very different for a well posed good problem. Is that clear? But for some of the problems where you lose quadratic convergence, it would take a long time for the problem to converge, or the error to go from 0.01 to say 10 to the power of minus 6. In many of these problems, especially in the commercial world, there is a tendency to reduce the convergence to 0.01 or even 0.1 and run the problem. It is possible that you may get some convergence immediately. But in most problems, if you tamper with the error, the problem will not forgive you, in the sense that in the next step you will not even get, or next step or after 2 steps, you will not even get to 0.01, or in other words, you will not even get a convergence for the error to be 0.01. In other words, the solution would start diverging. So what does it mean, in a very physical sense? In a very physical sense, I'll just plot it here. Suppose this is the graph, the stress strain curve that you should get, and if you now allow more and more error, in the sense that increase this value, okay, the solution would start diverging, and instead of following this path, you would follow some other path, okay, and the error would start accumulating. So it is not a good practice to run a problem by reducing the convergence requirements. Okay. It is usually 10 to the power of minus 6. Okay. Some research problems we use even 10 to the power of minus 8. Is that clear? So please do not reduce it and try to get a result. That will be, your happiness will be very short lived. You will not get it in the next 4 or 5 steps. Is that clear?
How to decide
How do you decide this number? That's what I said, that usually 10 to the power of minus 6. Usually 10 to the power of minus 6 is a good figure. Okay. If you want, you can reduce it to 10 to the power of minus 5, but you have to check whether it keeps converging in the rest of the steps. This 10 to the power of minus 6, yes, it is based on the experience of so many problems. Is that clear? That's why I said that many people use it 10 to the power of, even use 10 to the power of minus 8 to check how the convergence rate is for their algorithms. Right. Yes, that's a good question. Does it depend upon the machine? It depends upon two things. One is how good your KT is. In many of the nonlinear problems, it is possible that KT becomes what is called as ill conditioned. Okay, we will discuss ill conditioning later in the course, but KT does not behave very nicely, and the lambda max by lambda minimum, which is called as the condition number, okay, becomes quite large, and this interferes with the number of digits, accuracy of the results, or interferes with the number of meaningful digits. Okay. So, there is actually a relationship between the condition number and the accuracy of the machine. Many times if you use a 32-bit machine, you will get one type of accuracy, and as you increase it, you get another type, and so on. So, it is a combination of the condition number of k and the accuracy of the machine. If for some problems it may so happen that the first 5 digits, after the decimal, that may only be meaningful, the rest of it may be junk. Sometimes it may be 6, 7, and so on. This depends upon the condition number. We will talk more about it once we finish the first part of the lecture on nonlinearities. Is that clear? Yes. So, we will continue now with our second increment, starting again from the first iteration. Look at this carefully now, that f is not 2.4. No, it is not 4.8. Look at that. It is what is the sorry, f is 4.8. Sorry, the error is not 2.4. We started with 2.4 last time. F is 4.8, of course. Okay, and the first thing is notice that it is 4.8, and the error 2.401. Correct. So, the error is now 2.401. So, you have no escape. So, if you keep accumulating the error, anyway, next step you have to handle that guy. Okay, so, you have to add that to your error in this step, or the second step, or the second increment. We start with an error of 2.401. And now, what is the tangent stiffness? Yes. So, the strain you have to substitute for the previous case. Yes, you are absolutely right. The strain of the previous case you have to substitute, and substitute it here, and then tell me what would be the value of KT. Yeah. Have a look at it. It is last time it was 2.88. So, this time it happens to be 2.885. So, 2.885. So, now calculate du. Okay, now it is 2 and 1. And so, all these things would change. and what would be the value of du1 happens to be 0.832, right? Check that out, 0.832, right. So now delta u, note this, delta u is 2 and 1, that's only 2 and 1, so I remove all these guys here. So that happens to be 0.832. But there's a change in the epsilon calculation here. Of course, that remains to be the same. Sorry, I have to 2 1 and 2 1 happens to be and epsilon calculation here involves two quantities, this as well as my previous increment quantity as well. So what was my previous quantity? Delta epsilon, this is divided by 5 and that happens to be 0.167. 16. Yes, that's a very good question. What happens for the length change? Please note that we are looking still at a small deformation case. In other words, change in length is not very high, we are not taking it into account. That is the difference between an infinitesimal case and a finite deformation case. So 0.166. No, this is not a finite deformation case, it's an infinitesimal deformation case because we are not considering the length change. We are considering only material nonlinearity, you are absolutely right, and we are not considering the geometric nonlinearity as it is called. Okay, so we are considering only the sigma is equal to 20 into epsilon minus epsilon squared case. So calculate delta epsilon 1, and so this happens to be epsilon 1 2 happens to be 0.1394 plus 0.166, and that happens to be 0.306. So what happens to my sigma? So that is the first one, second, and so what happens to sigma? Yes, substitute that epsilon here, and so that happens to be 4.247. So still I have error because it's 4.8 versus 4.247. Okay, so I have to go to the next iteration in this increment. Right. So the error at the end of the first iteration in my second increment happens to be 4.8 minus 4.247, 0.553. So we'll stop here and we will continue with the second iteration for the second increment in the next class. Let us finish this problem so that you'll understand completely how we are doing. If there are any questions, we'll take it up in the next class.